Welcome to This Explainer. Today, we're diving into the fascinating rules that govern how energy flows and, well, why things actually happen in our universe. If you've ever wondered about the hidden math and logic driving literally every physical process around us, you are in exactly the right place. We're going to break down the laws of thermodynamics into a simple explanation designed specifically for beginners, but I promise you it is packed with some absolutely incredible insights. Let's start with a mystery I think we can all relate to. Over time, your bedroom is inevitably going to become a disorganized disaster zone, right? But unless you put in the physical work, it will absolutely never suddenly become neat on its own. Now, this might just seem like a frustrating fact of life, but it's actually a direct, everyday demonstration of universal physical laws at work. So here's our roadmap for today. First, we'll set the thermal baseline. Second, we'll look at conserving the universe's energy. Third, entropy and rising disorder. Fourth, the rules of spontaneity. And finally, the absolute zero limit. All right, let's jump right into Section 1, setting the thermal baseline, better known as the zeroth law. Now, you might be thinking, the zeroth law, that's kind of a weird place to start. Well, scientists actually realized this foundational concept was so crucial that it logically had to precede the first law. But before we get to the law itself, we need to quickly understand thermal equilibrium. Simply put, this is just when two things are the exact same temperature. Because they're the same temperature, there's absolutely no heat flowing between them. No energy flow means they are perfectly balanced. So the zeroth law gives us this beautifully clean logic. If two systems, let's just call them System 1 and System 2, are in thermal equilibrium with a third system, System 3, then they absolutely must be in equilibrium with each other. I mean, think about it. If the temperature of 1 equals 3 and 2 equals 3, then 1 obviously has to equal 2. It sounds incredibly basic, almost like common sense, but this transitive property is literally the entire foundation for how we define and measure temperature in the first place. Moving right along to Section 2, conserving the universe's energy, or the first law. This law gives us a super reliable way to quantify energy flow, and at its core, it's all about the strict conservation of energy. The big takeaway here is that energy is never just magicked into existence, and it doesn't just vanish into thin air either. It simply transforms. It shifts from potential energy waiting to be unleashed into kinetic energy in motion, or maybe into heat energy. Now, sure, physicists might tell you this gets a bit wonky down at the quantum level, but for general science and chemistry, this rule is absolute. To put some math behind this, scientists look at the change in a closed system's internal energy. Imagine a completely sealed box. We want to know exactly how the total energy inside that box changes during any natural process. And it boils down to this super simple equation. A system's internal energy changes based on only two things: the heat flowing in or out of the system and the physical work being done on the system by its surroundings, or vice versa. If heat flows in, the energy goes up. If the system does work on the outside world, it uses up some of that energy, so it goes down. It is basically the universe's perfect accounting book. Which brings us to Section 3, entropy and rising disorder. The infamous second law. Okay, so there's a catch. We know there are processes that completely obey that first law of conservation we just talked about, yet they never actually happen in nature. For instance, energy never spontaneously flows from a cold object to a hot object. Why not? Well, say hello to entropy. Entropy can be notoriously tricky to wrap your head around, but it's best described as disorder. It measures how dispersed the energy of a system is. This is exactly why heat spontaneously flows from your hot coffee cup into the cold table beneath it. The heat energy naturally seeks to spread out and become more disordered, rather than staying concentrated in your mug. To really grasp this, think of it like writing computer code. Imagine you're programming a simulation of an ionic solid. You'd need a massive amount of information to encode that rigid geometry, the precise distances between molecules, their exact configurations. It's incredibly ordered. But what if you're coding a liquid? The molecules are just randomly sloshing around. You basically just need to define the volume and the shape of the container. That requires way less information. And that brilliantly illustrates why increasing entropy, moving toward a more liquid, random state, is thermodynamically favorable. The universe just prefers less rigid coding. So, the grand takeaway of the second law is this absolute rule. The total change in entropy, meaning the system plus its surroundings, must always be greater than zero for any real process. The overall disorder of the universe is constantly, relentlessly increasing. If the entropy of your specific system goes down, it just means the entropy of the surroundings had to increase by an even greater amount to pay for it. Let's look at Section 4, the rules of spontaneity. But wait, this brings up a massive question. If the universe always tends toward chaos, how do highly structured, beautiful things ever happen on their own? How does order spontaneously form? To solve this, scientists use something called Gibbs free energy. It calculates if a process is thermodynamically favorable by looking at the change in enthalpy, which is the energy, the change in entropy, and the temperature. If the resulting Gibbs free energy is negative, boom, the process is spontaneous and just happens on its own. It's basically a grand tug of war between energy and disorder. As you can see in this matrix, if a process releases energy, meaning it's favorable, and it increases disorder, also favorable, it will always happen spontaneously. If both are unfavorable, never happens. But what if they disagree? Say you have favorable energy but unfavorable disorder. Well, in that case, temperature acts as the tiebreaker. Processes that create order can still happen spontaneously, but usually at lower temperatures, where the universe's penalty for creating that order is minimized. It's absolutely crucial we point this out, because you'll sometimes hear people incorrectly use the second law to claim that order can never happen spontaneously. That is simply not true. Systems can absolutely defy entropy and spontaneously create order on a local scale. It just requires the energy dynamics to be favorable enough to outweigh that localized drop in disorder. Let's look at a perfect everyday example, washing your hands. Dirt is nonpolar, so it won't mix with water. But soap molecules have a polar head and a long nonpolar tail. When you wash up, these molecules spontaneously organize themselves into highly structured little spheres called micelles. The tails face inward to trap the dirt, and the heads face outward toward the water. Now, forming this incredibly ordered sphere is technically a drop in entropy, but the favorable energy interactions between the polar heads and the water drastically lower the overall energy state. So the favorable energy wins, the micelle forms completely spontaneously, and your hands get clean. And finally, Section 5, the absolute zero limit, also known as the third law. We've talked energy, we've talked disorder, but what happens if we take temperature all the way down to its absolute minimum? Well, the third law states that if you have a perfectly crystalline solid at absolute zero, its entropy is exactly zero. At absolute zero, there is absolutely zero thermal motion. None. If the crystal is perfect, there is literally only one specific way for the molecules to be arranged. It is the absolute most ordered state a substance can possibly exist in. But there's a huge catch when it comes to that number zero, specifically 0 Kelvin. The third law also tells us that achieving the state of perfect stillness is physically impossible. We can actually prove this by looking at a theoretical concept called a Carnot heat engine. The math for this idealized engine's efficiency involves subtracting a fraction from the number 1. That fraction is the lower temperature divided by the higher temperature. Now, if that lower temperature were to ever actually reach absolute zero, the fraction itself becomes 0, and 1 minus 0 is 1. That would mean the engine operates at exactly 100% efficiency. And that perfectly illustrates the final limitation of our universe. Because a 100% perfectly efficient engine doesn't, and literally cannot exist in reality, that temperature fraction can never mathematically reach 0. Therefore, absolute zero itself can never actually be reached in any finite number of steps. Total, perfectly still order is an impossible, completely unreachable goal. Which leaves us with one final, kind of mind-bending thought to ponder. If reaching a state of zero entropy is physically impossible, and the second law dictates that the total disorder of the universe must constantly increase with every single passing moment, what does that mean for the ultimate, long-term thermodynamic destiny of our entire universe? Thank you so much for exploring the fundamental rules of reality with us in this explainer, and keep questioning the incredible mechanics of the world around you.